Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 1 on similar right triangles. Now you might think to yourself, we just got done with Unit 7, which was all about similarity. We even ended Unit 7 with discussions about similar right triangles that are created when we drop an altitude from the right angle of a right triangle to its hypotenuse. Well, Unit 8 is all about similar right triangles as well, except we're not going to be looking at it by dividing one right triangle into two other similar right triangles. We're going to be looking at separate right triangles that are similar to one another and what we can tell about the ratios of relatively positioned sides. Let's get into that right away to see what I'm talking about. Now, in our last unit on similarity, we saw conditions that create similar triangles and properties of similar triangles, such as the fact that corresponding angles are congruent and corresponding sides are proportional. In this unit, we will be concentrated almost exclusively on similar right triangles. So let's take a look at exercise number 1. Consider the two right triangles shown below not drawn to scale. Letter A. Justify why triangle ABC must be similar to triangle DEF. All right. Well, remember, we had three ways that we knew that triangles were similar to one another. We had the angle-angle theorem, we had the side-side-side theorem, and we had the side-angle-side theorem. All right. Two of those three would be applicable here. Pause the video now and see if you can think about how to justify that these two triangles are similar to one another. Well, one thing that we can see right away, right, is that every side of triangle DEF is simply twice every side length of ABC, and therefore they must be similar by the side-side-side similarity theorem, right? We could also say that because DE is twice AB, and because FE is twice BC, and because the angles in between them are congruent, i.e. 90-degree angles, they're similar by the side-angle-side theorem. All right, but mostly it's really about that side-side-side theorem for similarity, not for congruence, obviously, right? So I'm just going to say triangle DEF is triangle ABC after a dilation by a scale factor equal to 2, right? So they're similar. It's really the side-side-side theorem. Now, we've worked a lot with ratios of sides in similar triangles. We've almost always been looking at, one of these sides divided by one of these sides is equal to one of these sides divided by one of these sides. What I'd now like to look at, though, is ratios within the triangles themselves. So let's take a look at that in letter B. Determine the values of each of the following ratios. Express your answers in simplest form. All right, so you shouldn't need my help with this, all right? All I want you to do is set up each one of these fractions and, if you can, reduce the fraction to its simplest form. Pause the video now and take a couple minutes to do that. All right, simple enough, right? BC divided by AB, that's easy enough. Right, that's just going to be 3/4, and there's nothing we can do to simplify that. BC divided by AC is going to be 3/5. Again, nothing we can do to that. And then AB divided by AC is going to be 4/5, and again, nothing we can do to simplify that. So simple enough. Now we skip over to this larger triangle, and we've got EF divided by DE. Well, EF divided by DE is 6 divided by 8. But of course, we can reduce both the numerator and denominator by a factor of 2, and we get 3/4. EF divided by DF is going to be 6/10, and again, just like before, we could reduce each of those down to 3/5. And finally, DE divided by DF is going to be 8/10, and we can reduce each of those down to 4/5. All right, simple enough. And you can probably see the point, right? Each of these two ratios is equal to 3/4. Each of these is equal to 3/5. Each of these is equal to 4/5. All right? And what we're getting at here is in that last exercise, we saw that the ratios of relatively positioned sides within two similar triangles are equal. All right, this is true regardless of whether the triangles are right triangles or more general types. It makes no difference. All right, now again, we've looked so far at ratios of corresponding sides, and that's where I say, okay, this side divided by this side is equal to this side divided by that side. I'm now saying if I take, let's say, AB and I divide it by AC, I'm going to get the same thing as if I get DE divided by DF. Now that might seem awfully intuitive and it might seem obvious, but it's different than what we've seen so far. So let's actually prove that now in exercise number 2. In the diagram below, triangle DEF is a dilation of triangle ABC by a scale constant equal to K. Algebraically prove that DE divided by EF is equal to AB divided by BC. All right, so in other words, I want to now show that the ratio of similarly oriented sides or relatively positioned sides is equal between the two triangles. So if I do DE divided by EF, I get exactly the same thing as AB divided by BC. Let's do this proof together, and let's just start off by writing down DE divided by EF. Right? And what is that equal to? Well, we know that that triangle, right, this one is just the smaller triangle that's been scaled by a factor of K. So what is DE? Well, it's K times AB. And what is EF? Well, that's K times BC. Okay, that is literally what it means to dilate this triangle by a factor of K. Now, we can take this particular fraction and we can break it up. We can break it up into K divided by K times AB divided by BC. Okay, just like when you multiply two fractions together, you multiply their tops and multiply their bottoms, you can unmultiply two fractions by sort of breaking them into a product that looks like this. Now, any number divided by itself, except for 0, is equal to the number 1. So K divided by K is equal to 1. So we have 1 times AB divided by BC, and any quantity times 1 is just equal to itself. So we see that DE divided by EF has to be equal to AB divided by BC. The ratios of relatively positioned sides amongst two similar triangles, regardless if they're right triangles or not, is always going to be equal. All right, let's play around with that a little bit. Exercise number 3. It is known that triangle MNP is similar to triangle EFG. If MN is 10, NP is 6, and MP is 14, then which of the following is the ratio of EG to EF? All right, pause the video now and see if you can figure this out based on what we were just talking about. All right, I like a good picture for this. It doesn't even have to be accurate. All I want is two triangles that look similar. It doesn't matter which one is the larger one and which one is the smaller one. I'm going to call this MNP, and this is EFG. All right. Now, what do I know? I know MN is 10. Let me just move this a little bit. I know NP is 6, and I know MP is 14. Now, I can't say that EF is 10, FG is 6, and MP is 14, right? These two triangles are not congruent. They're just similar to each other. But if I need the ratio of EG to EF, right? EG divided by EF, that is going to be the same as MP divided by MN, right? So again, EG divided by EF is going to be the same as MP divided by MN, in which case MP divided by MN is 14/10. I can divide both of those by 2, and I find that that must be equal to 7/5. All right? Now again, I have no idea what the side lengths of EFG are. They could be larger than MNP, they could be much smaller than MNP, I don't know. But what I do know is the ratio of EG to EF has to be identical to the ratio of MP to MN because the two triangles are similar. Now, we can use ratios of relatively positioned sides or the ratios of corresponding sides to solve a variety of real-world problems, okay? So let's take a look at exercise number 4. A person who is 68 inches tall casts a shadow that is 54 inches long. At the same moment, a tree standing vertically casts a shadow that is 18 feet long. What is the height of the tree in feet? Round to the nearest foot. Draw a diagram to show how you solve the problem. All right, well, now you get to see my great artistry, right? Let's start with the person, right? We've got a person who needs to eat more, all right? And this person stands 68 inches tall, all right? And the sun casts a shadow with that person that is 54 inches long. Okay, so I got my person 68 inches tall with a shadow on the ground, right? 54 inches long. Now at the same time, all right, we've got a tree. Must be the middle of winter. All right, whose height I do not know, so I think I'll call that H. All right, which casts a shadow that is 18 feet long. Now the idea is that the triangle formed by the person and the shadow is similar to the triangle that is made by the tree and its shadow. And the reason for that is that there's assumption that this is a right angle and that this is a right angle, and the angle of elevation of the sun, because it's happening at the same time, is the same, so that angle and that angle are the same. Now what we can do is we can use that ratio of relatively positioned sides, and we can say H divided by 18 is going to be 68 divided by 54. All right, now don't get me wrong, this is using ratios of relatively positioned sides in the two similar triangles. You could have also said H divided by 68 is equal to 18 divided by 54. That would have worked as well. Because at this point, what we're going to do is we're simply going to cross multiply, right? And we're going to get 54 times H is equal to 18 times 68. And for that, I definitely want to bring out my calculator. Right, so I'm just going to have a little 18 times 68, and that's going to give me 54 times H is equal to 1,224. And now we'll just do a little division by 54 to figure out the height of the tree. Ah, of course, that still didn't work. 1,224 divided by 54. There it is. 22.6 repeated, which means the height of the tree rounded to the nearest foot is 23 feet. All right, simple enough, right? So this is often the way a lot of similarity problems work out. In other words, people find it maybe a little bit more comfortable to stay within a triangle when setting up the ratio, right? This side divided by this side of that larger triangle is equal to this side divided by this side on that smaller triangle. But again, as I mentioned, it would work just fine to do H divided by 68 is equal to 18 divided by 54. The cross multiplying would all get you down to here anyway, and you'd still get 23 feet. Let's take a look at another one. Exercise number 5. A rectangular picture has a width of 4.5 inches and a height of 3 inches. The picture is scaled up in size such that the new width is 6 inches. After scaling, what is the picture's new height? What is the length of its diagonal to the nearest tenth of an inch? Okay, so there's two questions here, right? What is the picture's new height? And then, what is the picture's diagonal length? Pause the video now and see if you can solve both of these. All right, well, let's get a good picture. All right, so we have our original picture that is 3 inches by 4.5 inches. Okay. And then this thing got scaled up so that its new width is 6 inches, and we don't know the new height, and we don't know the new diagonal. Okay, so we've got our original and we've got our scaled version. Okay, and it doesn't actually matter that it's not a triangle, that it's a rectangle, because it did, and again, the relative positions, right, relative size is the same. So the first thing I want to know is that height. So I can now say h divided by 6 is equal to 3 divided by 4.5. So h divided by 6 is equal to 3 divided by 4.5. All right, I'll do some cross multiplying. I'll get 4.5 times h is equal to 18. Divide both sides by 4.5. This is pretty common. All right, and my h will end up being 4. And again, you can check that on your calculator, but that one I can actually do in my head. All right, so my new height is equal to 4. Now, in terms of my new diagonal, that I'm not going to use similarity for at all. I'm just going to use the Pythagorean theorem, right? Because I'm working within a rectangle. That means that's a right angle. I now have a 6-inch and 4-inch set of legs, and therefore I just need my hypotenuse. So I can say that 4 squared plus 6 squared is equal to my diagonal squared. That's going to be 16 plus 36 is equal to my diagonal squared. All of this is going to be 52 is equal to d squared. And here's where I definitely need my calculator, because I don't know what the square root is of, oh no, that didn't work. Let's do this. I want to just clear some stuff out. Square root of 52. And my new diagonal length to the nearest tenth is 7.2 inches. All right, there we are. Cool. All right, let's take a look at one last problem. Exercise number 6. One of the classic engineering uses for similarity is the measuring of the width of a river, which is not easy to do with a tape measure. To do this, engineers spot 2 points on opposite sides of the river, A and B. They then measure the distance of BD along the river and then a length of DE perpendicular to the river as shown. Finally, they draw a line from A to E and mark the intersection point of AE and BD as point C. Wow. Okay, so let's just make sure you've got this, right? Now, I realize these days, to measure the width of a river, engineers would probably take a GPS picture of the river with some kind of scale on it and do it that way. But it used to be before you had easy satellite imagery, the way that we've gotten it in the last 10 to 15 years, what engineers would do is if they wanted this width, again, what they would do is they would first spot 2 points that are on opposite sides of the river. Okay, those are A and B. All right, then they would measure some distance along the river, from B to D. They'd measure then a distance on this side of the river, which is easy enough to do. And then they'd kind of spot a line from point A to point E and mark its intersection point like that. Okay, all that being said, now letter A, explain why triangle ABC is similar to triangle EDC. Pause the video now and see if you can justify that. All right, well, it's simple enough, right? Here we go. Angle B is congruent to angle D because they are right angles, right? So first off, B and D are right angles. There they are. But we also know these two angles have to be similar. So angle BCA must be congruent to angle DCE, and I said those angles have to be similar. Those angles have to be congruent because they are vertical. Okay, and therefore, nice 3 dots, triangle ABC must be similar to triangle EDC by the angle-angle theorem. All right, so it's our classic angle-angle theorem of similarity between these two. Okay, So now let's figure out the width of this river. Letter B. If BD is equal to 225 feet, CD is equal to 30 feet, and DE is equal to 12 feet, then find the width of the river AB in feet. All right, so let's take a look at what we know. And again, think about this, right? If I'm trying to find the width of a really wide river before satellite imagery and things like that, it would be easy enough to find the length here. It would be easy enough to find this length here. What would be hard is figuring out the length across the river. I mean, again, tape measure, not easy to do. So what do we know? At this point, we know that BD is 225 feet. We know CD is equal to 30 feet, and we know DE is equal to 12 feet. See if you can figure out what the width of the river is, AB, in feet. All right, well, what I really need is I need some measurements along triangle ABC. And I do know that BD is 225. I really need BC, right? So the first thing I want is I want the length of BC, and that's easy enough. BC is going to be 225 minus 30, which is going to be 195 feet. All right, so this just here is 195, okay? So now what I can do is I can say that AB divided by that 195 is equal to 12 divided by 30. Right, let's take a look at that really quick, right? So now I'm using those ratios of relatively positioned sides. AB divided by BC is equal to ED divided by CD, right? And now, of course, I know everything I need. I just have to do some cross multiplying. 30 times AB is equal to 12 times 195. And I don't really even need to know that product. I could just now divide both sides by 30, and AB is going to be equal to 12 times 195 divided by 30. And the width of the river is going to be 78 feet. And that's it. And this was actually the way that they measured distances across rivers or other things that were hard to find distances across, right? Again, very difficult to stretch a tape measure across a river. On the other hand, easy enough if you're on one side of the river to measure this distance and that distance, and also pretty easy to spot where that point is going to be here. All right, let's wrap this up. Now, today what we did is we looked at similar right triangles, but really what we looked at could be applied to any similar triangles. This idea that now we can look at not just the ratio of corresponding sides, but the ratios of relatively positioned sides in two similar triangles. And because those kind of dilation constants just cancel out, the ratios of relatively positioned sides are going to always be equal within two similar triangles. And that is going to really be key to everything else we do in this unit. In our next lesson, we're going to see how that gets applied and how that gives birth to what is known as right triangle trigonometry. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.